In this video, we look at Unit 3 test review for chapters 5 and 6. So chapter 5 is when we got into probability, but using a discrete probability distribution. And in section 1, we looked at what was the foundation of a discrete probability distribution. And so for questions 1 and 2, it's kind of bringing back that information that you were introduced to in the beginning of the unit. And question 1 wants you to determine the following distribution. It's not a probability distribution, and it wants you to be able to determine why. So for this question, we have to remember, what makes a probability distribution? Well, there's two things that we know: the sum of the probabilities have to equal to 1. So if we add these numbers together, we should get 1. And if that is true, then the second thing, each probability should be between 0 and 1. If there is a probability that's not between 0 and 1, or the sum is not equal to 1, then it's not a probability distribution. It has to be, or I should have said and, not or. If 1 and 2 is not satisfied, then it's not a probability distribution. And here we see a negative value. So that negative value indicates that this is not a probability distribution. When you add these 5 values together, you do get 1, so that checks off. But this value is not in between 0 and 1, so the probability cannot be negative. Now, for question number 2, still section 5.1, we look at, can we calculate probability from a discrete probability distribution? So it says the following table represents a probability distribution of the number of vacations taken last year for a randomly selected chosen family. Find the probability that a family took at least 3 vacations. Well, we want to know what at least means. My statement is the probability that x is greater than or equal to 3. So it can be 3 or 4, and the word or tells us that we can add the values together, or add the probabilities together. So we want the probability of 3 vacations plus the probability of 4 vacations, which is 0.1 plus 0.04, which is 0.24, or 0.14, sorry. So there's a 14% chance that a family took at least 3 vacations, which is an unlikely event, right? We talked about that in the beginning of Unit 2. So as we transition from section 1 to section 2, we start to take a probability distribution and calculate a mean, and calculate a standard deviation, and calculate a variance. So the first question is more so simple. It says compute the mean of a random variable with the given discrete probability distribution. And if we recall from section 2, the mean is the sum of each probability times its discrete random variable, the value of that random variable, and that will give us the mean value. That's the value that we expect to get after many trials of whatever this probability distribution represents. And in this case, once we multiply those values together, negative 0.5 times 0.2, and then 5 times 0.3, and then 20 times 0.1, and 35 times 0.4, we get these products, and we take those products and we find the sum, and that represents our average. So in this case, the average is 16.5. And there's no context, so I can't really give a meaning to that value. It's just the average is 16.5. So whatever this distribution represents, for many trials of this distribution, on average, this is the average value we expect to get based on the probability distribution. And for number 4, it's more or less similar, so we will be able to talk about meaning because this particular distribution represents the number of vacations. So it's like that previous problem. This time we want to use this distribution to calculate the standard deviation. So the following table presents the probability distribution of the number of vacations, x. So each of these values are number of vacations taken last year for a randomly chosen family. Compute the standard deviation, sigma. So there's a lot of background information you need to know in order to complete the standard deviation, to compute it. In order to compute the standard deviation, then you have to find the mean, right? The mean is what we just looked at previously. It's the sum of the discrete random variable times its respective probability. And then after you find that, you have to find the variance, which is the sum of that discrete random variable squared times the probability minus the mean squared. And then after we find that value, then we can take the square root of that to get the variance. So there's a lot of things you have to be able to, there's two different steps you have to complete in order to get the answer, which we need is the variance. So to find the mean is what we did previously. All right, so I'm going to take each x value times its probability. So 0 times 0.15, 1 times 0.53, or 0.63, dot, 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 all the way up to the last value, which was 4 times 0.02. And that will give me the mean. And in this case, it was 1.9 vacations. So for many, let me go back here. For many selected families, we start choosing random families and ask them how many vacations, and we keep doing that. For many selected families, this is the average number of vacations that we expect to get from this distribution. So 1.19 vacations. Now I have to find that value first because that value is crucial in the calculation of the variance. The variance is sigma squared, which is necessary to find the standard deviation, which is the square root of that value. So now we more or less repeat this process, except we need to square the x values. So x squared plus the probability. And when we did this in previous, or when I did this in previous videos, I made like a little table. So I'm gonna make that over here. I have x squared times p of x. So 0 squared times 0.15, 0, 1 squared times 0.63, 0.63, and then we complete that process so we can get all the values, so then we can find the sum of those values. This is more or less the process we take to get that information in order to calculate the variance. So the variance squared is the sum of this information minus the mean squared. So we take all those numbers that is highlighted in yellow, which is the sum is 2.15, and we subtract 1.19 squared, and we get 0.7339, and that is the variance. Now we need the variance in order to calculate the standard deviation. So next we get the standard deviation, we square root that number, and that will give us a standard deviation, which will be 0.857 vacations. And what is that number? So if we think back to even the previous unit when we talked about, well, really unit 2 when we talked about measures of variation, this is the typical spread from each value. It is from the average. So when we look at the number of vacations, they tend to vary about 0.857 vacations from the mean number of vacations, which is 1.19. So it just tells us a typical variation for this particular data set. So that's 5.2. And then we transition into 5.3, which gets us back on probability. So 5.1 was discrete probability distribution. What is it? How we can use it to find the probability of an event. 5.2 was calculating the mean, the expectation, the variance, the standard deviation, and then 5.3 gets us back on probability, but we look at the binomial distribution. So in this particular problem, it says it is estimated that 45% of households own a riding lawnmower. A sample of 12 households studied. What is the probability that more than 9 of these households own a riding lawnmower? So when we talked about the binomial distribution, there were 4 things that we were looking for, and just to kind of go over those again. So the first thing was, are there 2 outcomes? In this case, there are 2 outcomes. You either own a lawnmower or you don't own a riding lawnmower. So that would be your success and failure. The second is there a fixed number of trials? In this case, it's the number of people that has been selected. So there's only 12 households being selected, so that's a fixed number. You're not continually selecting households until you find your desired result. You're only choosing 12, and that's it. And then independent. Are the households independent of each other? Well, in this particular situation, we are sampling without replacement, so that from what we talked about before, you would think, oh, well, that could be dependent because we're selecting households, so we're not putting them back. However, we are sampling less than 10% of the population, right? If 45% of all households have a riding lawnmower, and we're selecting 12 people from the population of everyone who has a riding lawnmower, then that's less than 10% of the population. So you don't really have to worry about any of these 4, but it is nice to kind of review like what makes this a binomial setting, and these 4 conditions make it a binomial setting. So this situation is an independent situation. And then lastly, we look at, well, is the probability of a success, which is owning a riding lawnmower, the same for each trial? And it's 0.45. It's the 45% likeliness that a household has a riding lawnmower. So each of those sample of size 12, they have the same likeliness of having a riding lawnmower. It's 0.45. So then we look at, well, how do we calculate the probability? And we had a formula for that. The probability of our distribution of x, which is the number of people that have a riding lawnmower, is NCX, which is a combination, which represents the number of individuals who have a riding lawnmower out of the sample, like the different ways you can select those people, and then the probability of a success to the power of x times the probability of a failure to the power of n minus x. And so in this case, our n is 12, our p is 0.45, which is our probability of a success, which means q, which is a probability of a failure, which is not owning a riding lawnmower, is 0.55. 55% of the people do not own a riding lawnmower. And then x comes from what the value that x represents comes from what we want the probability of. So if we want the probability that more than 9 own a riding lawnmower, well, more than 9 would be 10, 11, and 12. So we would have to calculate in our event the probability that x is greater than 9. That would be x can be 10, or x can be 11, or x can be 12. And then we've known from a previous unit, in unit 2, that anytime we have the word or, it indicates addition. We want to add those probabilities together. So to calculate probability of 10 riding lawnmowers, well, that's 12 choose 10, and then 0.45 to the 10th power and 0.55 to the second power. If we kind of remember that the 2 values in the parentheses, that's my p and my q, has to add up to 100% or 1, and then my exponents have to add up to 12 because it's 10 individuals with a riding lawnmower and 2 households without a riding lawnmower. And then this is just a value that we would be able to calculate. So if I go to Desmos, we can use the combination feature here. So we can do n capital C and R and do 12 comma 10, or if you would prefer, you can do the formula that you've learned previously, so that works as well. So same value, 66. You can put everything together. So I could do 66 times 0.45 to the 10th power, and then 0.55 to the second power. Or I can even take this NCR along with this information and just put those together, same value. So you have a lot of flexibility in how you can, and you can even take this too. So let me show that. Copy and paste, or copy this too. So 3 different ways to calculate this, and you get the same answer. So you have to figure out, in which way works best for you, what's going to help you be more successful. But we have to do this 2 additional times to find the probability. This is the probability that 10 people have a riding lawnmower, 10 households have a riding lawnmower. So we want to do the same thing for 11 and for 12. So I'm going to round it 0.068, and then we do 11. So 12 choose 11, 0.45 to the first power, and then 0.45 to the 11th power, and then 0.55 to the first power. And when I go back to Desmos here, I'm more likely to probably do this one myself, even though I know how to do it the other ways, because I only have to change 3 numbers. So that's 11, this is 1, and this is 11. So I only have to change this number, and this number. It's not too difficult to change the other numbers too, but I mean, I've only have to change 3 numbers instead of 4. So I guess a few keystrokes, save my fingers a few keystrokes. But so now I have the value. I'll go back here and 0.00101, and then we do 12. So 12 choose 12, 0.45 to the 12th power, 0.55 to the 0th power, and then let's see what that is. Let me go back. So change this to a 12. Change that to a 2. That to a 0. So that's essentially 0. But I went ahead and wrote out some of the decimal places. So, and we add these values together, and we get the probability that the probability that more than 9 households own a riding lawnmower is about 0.78%, or 0.00788. I guess that's 0.79. But that's a very unlikely event for that to occur. So let's look at another example in which we can use table B for the binomial distribution, where we can also use a formula as well. So again, section 5.3. In a large bag of marbles, 25% of them are red. So immediately we know that this is the value of P, or it could be the value of P. We don't know yet what they want the probability of, but I know that that's the value of P. I probably should wait, but so the probability of a success is 25% of them are red, which means the probability of not getting red is 75%, or 0.75. So a child chooses 4 marbles from the bag. If the child chooses the marbles at random, what is the chance that the child gets exactly 3 red? So because we want to get red marbles, then the probability of a success has to be related to red, that's why we can say that P is 0.25. So we know that we want the probability that it's exactly 3, not less than 3, not more than 3, just exactly 3. So we only have to find one value, unlike the previous example where we defined 3 values and add them together. So the probability of exactly 3 red marbles would be 4 choose 3, 0.25 to the third power, and 0.75 to the first power. And then this, remember, the two values in the parentheses has to add up to 1, 25% and 75%, so 100%, or 1. And then the 2 exponents have to add up to the number of trials. So 3 for the success, 1 for the failure. That gives us 4. And if we calculate that, that will give us 0.47. Just utilizing our calculation that we did earlier in Desmos. So if I go back to Desmos and I have the value calculated here, this gives us 0.047 if you round it accordingly. Now in table B, if you notice up top here, 0.45 in that first problem was not in the table, so we couldn't use the table to find the probability. But 0.25 is, and so we can use this to find the probability. We just have to go to number of trials. So, and I'll zoom in here. There were 4 trials, and we wanted 3 successful outcomes, and 0.25 would be a probability of 0.047. So about a 4.7% chance that the child gets exactly 3 red marbles when she selects 4. So we get the same value. So you also can default back to the table as long as the probability of success is a value in the table. So keep that in mind as well. Now for number 6 is where for number 7 is where we transition into chapter 6, which was a continuous probability distribution and also a different table. So and there's 4 problems here, 7, 8, 9, and 10. So at a large department store, the average number of years of employment for a cashier is 5.7. So immediately when we read that, that's my mu. That's the population average with a standard deviation of 1.8 years. So that's my sigma, and the distribution is approximately normal. We want to see that so that we can use table E, and then we can also draw the normal curve. So if an employee is picked at random, what's the probability that the employee has worked for the store for over 10 years? So in this case, we look at, this is our probability statement. We're looking at an individual, so one employee, that their service is over 10 years. And so we want to figure out what that is. So first, we need to find the z-score, right? Because we know this is normally distributed, or approximately normal, that means we can use table E to find the probability. To use table E, we need a z-score. So to find the z-score, we take the value minus the mean divided by standard deviation. We get 2.39. We always round it to the nearest 10th, 2 decimal places. Second, we draw out our distribution. So make your bell curve mark off where it is you think the 2.39 is, and then we shade the appropriate area. We want more than 10 years, so we shade in to the right, and then we look for this probability in the table. So if we, and that's the third part, use table E. So if we go to table E, and we look for positive 2.39, so here's 2.3 and 9's at the very end, it's over here, 0.9916. When I go back to my distribution here, it doesn't look like I shaded in 99% of the graph. So we have to remember that that table only gives me the area to the left. So when I'm calculating my probability here, it's 100% of the area under the curve minus the area to the left, because the probability I want is the area to the right. So minus 0.9916, which is 0.0084, or 0.84%. So that's a very unlikely chance that if a worker is picked at random, they've been at the store for over 10 years. All right, for our second example from chapter 6, says Mrs. Smith's reading class can read an average of 175 words per minute. So that's my average reading time for the whole entire class, is like my population average, with a standard deviation of 20 words per minute. That's my sigma. The top 3% of the class is to receive an award, a special award. What is the minimum number of words per minute? So minimum number of words implies we're looking for a value. So since we're solving for a value, we use a different equation. X equals z-score times sigma plus mu, or X equals the standardized score times the standard deviation plus the mean. So they can read, we want to figure out what that minimum score is, X of words per minute a student would need to read in order to get an award. So when it says assume the data is normally distributed. So what can we do? We can look at drawing the distribution, figuring out what it means to be in the top 10%. That means if this distribution represents 100% of all the students, we're looking for what score would someone need to be at to be in the top 3%. So they would have like the very last score, and then everybody above them is 3%. That person, everybody above them, is 3% higher than everyone else, or 97% of the class is below them, is another way of looking at it. So then we look at, well, that little black portion is 3%. So in order to use this formula, I need to know the z-score. In order to find the z-score, I need to be able to look within the table and find the area. So we know the table only has the area to the left. So that means I really won't be looking at 3%. I'll be looking for the number closest to 97%. And so we go to our table, and I want to find in the body of the table what numbers are closest to 97%, and that would be, let's see, here's 0.9699, so it looks like 1.8, and that should be 8. So the number closest to 97% is 1.88. Now, we should expect a positive z-score because we're above 0. So that is an indication of, oh, that's correct, because it's above 0. That's what we want to see. So now we can utilize our formula, substituting the appropriate values, 1.88 times 20 plus 1.75, 212.6. If, let's say we need to round that to the nearest whole number, it's approximately 213 words per minute. So a student who read 213 words per minute or more would be in the top 3%, and they would get an award for the class. All right, so our next example says the mean annual income for people in a certain city in thousands of dollars is 43, so mu is 43, with a standard deviation of 29, sigma is 29. A pollster draws a sample of 41 people. That means now we have a sample size. What is the probability that the sample mean income is less than 42,000? So this is a little different because the previous two were about an individual. It wasn't about a mean for the distribution. So for this particular one, our probability statement is X bar now, because that's for a sample mean, is less than 42,000, but we don't put 1,000, we just put 42. And we have to think about, is this normally distributed? how do we know? Because the only way we can find probability so far from a continuous distribution is using the table E, which is for normal distribution. How do we determine if a distribution is approximately normal for a sampling distribution? Well, we look at the sample size. Since the sample size is greater than or equal to 30, because it was 41, that means we can assume that the distribution is normal by the central limit theorem. It's approaching normality because the sample size is large enough. So we still calculate our z-score, value or mean, sample mean minus population mean divided by sigma, which is divided by square root of n. So 42 minus 43 divided by 29, which is divided by square root of 41, and we get negative 0.22. We draw out our distribution, try to figure out where might negative 0.22 fall at, and then we shade to the lower than side or to the left because we want the sample mean is less than 42, and this is the relative position that the sample mean is compared to the population mean. So then we look, and again we can look at table we look at table E to find the value. So if I go to table E and I go to negative 0.22, here's negative 0.2012, so there 0.4129 will be the area to the left, and subsequently as the probability. So 0.4129. There's approximately a 41% chance that the sample mean is less than $42,000 based on the information provided. And for the last problem in the exam review, it says a certain model car has a mean gas mileage of 28 miles per gallon, so our mu is 28. With a standard deviation of 5 miles per gallon, sigma is 5. It says a pizza delivery company buys 37 of these cars. That's our sample size. What is the probability that the average mileage of the fleet is between 27.2 and 28.2 miles per gallon? So my probability statement, 27.2, the average, so once the average is between 27.2 and 28.2, and again, because the sample size is large enough, that means we can use a normal distribution by the central limit theorem. What we need to do is, in order to use that normal distribution, we got to find some z-scores. In this case, we got to find two z-scores. So the first z-score comes from the 27.2 miles per gallon. So take that average minus the mean, that's population mean, divided by the standard deviation, which is divided by the sample size, and then that will give us negative 0.97, and then we find the other z-score because we're looking for the area between, which is also the probability. Take that 28.8 minus 28 divided by the same thing, and we get positive 0.97. Hopefully you're like, okay, that makes sense, because this value is 0.8 below 28, and this value is 0.8 above 28. So they should be the same. They should have a similar z-score value, just one is below and one is above. So second thing, draw a distribution. So we can draw a normal curve. We can mark off where we would think that would be. Since both of those values are, certainly close to -1 and +1, then we can, almost estimate that the area between will be close to 68%. We know that approximately 34% of or 68% of the data is within one standard deviation above and below. So we would expect to get a probability close to 0.68 or 68%. So we need to go to table A, look at those z-scores and get the areas so we can figure out what to do with that number. So up negative 0.97, so that's here, 0.1660, and then positive 0.97. Did I say 1.97? Yeah, so here's 0.9, and then 7 is here, 0.8340. So when we go back to our problem, the area to the left of the negative z-score here, so the area to the left of this one is 0.1660, so about 16%, about 17%, and then the area to the left of the other side is 0.8340, and so that includes the white and the blue. So when we want to find the probability, we only want the blue space, so we have to subtract those two numbers from each other. 0.834 minus 0.1660. So, and again, the answer we get is very close to 68%, 0.67 in fact, or 67%, because we know that within one standard deviation, from what we talked about in the very beginning in section 1 of chapter 6, that all data that represents a normal distribution within one standard deviation is approximately 68%. So these are the type of questions you'll see in your Unit 3 exam. So hopefully pay careful attention to the video and write some things down, and you utilize that to help you with your exam.